Over 200 million miles away from Earth, OSIRIS-REx is preparing for NASA's most ambitious sample return since the Apollo program. After months of detailed analysis of Bennu's terrain, the team selected the Nightingale crater as the sample site for the mission. OSIRIS-REx will need to carefully dodge rocky hazards as it descends to a space no larger than a few parking spots. The spacecraft has mapped the terrain in high resolution, capturing a stunning catalog of images across Bennu's rough surface. And now, we are ready to target Site Nightingale for the touch-and-go sampling event.
In the dark voids of the solar system, drifting in between the familiar planets and their families of moons, are the asteroids. There may be 1 million, perhaps 2 million of these cold, dark rocks. But these small worlds are anything but dull. In fact, some of them are time capsules from the very beginning of the solar system, unaltered for billions of years. And in fact, the clues to how everything around us began, from the formation of the planets to the beginning of life itself, may be locked up in these asteroids. And tonight, a spacecraft from Earth is going to touch one, bring back a sample, and prepare the long journey back to Earth where we can analyze it. Welcome, everyone. I'm Michelle Thaller from NASA's Goddard Space Flight Center, and thank you for joining us. I'm speaking to you live from the mission support area at the Lockheed Martin Space in Littleton, Colorado. As you can see, I'm struggling with my mask here a little bit. We're here to follow the sample collection for NASA's OSIRIS-REx mission. This is an operation referred to appropriately as TAG. Now, remember that this is a historic event. Today's endeavor will be the first time the space agency has ever touched the surface of an asteroid, collecting a sample of this pristine ancient material, a scientific treasure far more precious than gold. Joining me throughout the show will be the principal investigator of the OSIRIS-REx mission, Dante Loretta. Welcome, Dante.
Thank you, Michelle. It's really great to be here today. I'm a professor at the University of Arizona, and I have the honor and the privilege of leading this amazing mission for NASA and really for the world.
It's pretty amazing. So now the main event is happening in about an hour. And this is called TAG. Can you explain to us a bit why it's called TAG?
Yeah, today we're tagging an asteroid, and TAG is an acronym that describes our sample collection strategy. We're going to send the spacecraft down for a short duration contact with the asteroid surface, anywhere between 5 and maybe as long as 15 seconds. So we call it a touch and go, or tag an asteroid.
And it actually is almost sort of like a quick touch, a tag. It's a very good way of putting it.
Exactly.
Yeah, absolutely. So there's lots of asteroids out there. We talked about the fact that there are a couple million. So why have we selected this particular one to sample?
Yeah, the target of our mission is called Asteroid Bennu. And when we were designing the mission, we had to consider both engineering constraints and, of course, our science objectives. And when we looked at the capabilities of our spacecraft, we knew we needed to go what was called a near-Earth asteroid. So we were basically looking at its orbital properties and its location within the solar system. We needed an object whose orbit was pretty similar to the Earth so that we could launch off of our planet, rendezvous and spend some time at the asteroid, and then leave and bring this precious scientific cargo back to Earth.
Absolutely.
And then from the science perspective, we're really answering some fundamental questions. Why are we here? Why is Earth a habitable planet? How did the origin of life occur? So we wanted an asteroid that we thought was rich in water, that may have brought the oceans to our planet, and also rich in carbon. We're looking for the organic seeds of life that may have led to evolution as we know it today.
And this is really an amazing point, our connection to these asteroids. So what you're saying is that some of the organic compounds in my body, some of the water in my body right now, may originally have come from asteroids.
Almost certainly. The Earth was accreted from these asteroids. Bennu is a remnant that survived that process, but it's the geologic history of our solar system that's locked inside this body.
Absolutely. Now, there are many other asteroids like Bennu in the solar system, and of course there are some that are even larger. Over the last decades, we believe we have found nearly all of the potentially dangerous ones. Oh, we'll pause.
OREX natural feature tracking system has resumed processing. Position uncertainty is 1.6 meters.
Excellent. So getting back to my point, we know there are others out there that we have not yet detected. You know, in fact, just this past August, a truck-sized asteroid missed the Earth by less than 2,000 miles, and nobody even knew it was headed our way until it already passed us by. So for our survival, it's essential that we understand what's out there in our environment in space. And this is one of the main objectives of the OSIRIS-REx mission. we'd like to go out and meet Bennu before something like Bennu comes and meets all of us. So Dante, what can you tell us about this idea of planetary defense?
So as a result of Bennu having this optimal orbit for sample return, it also is what we call a potentially hazardous asteroid. Because its orbit literally does cross the orbit of the Earth, and there's a probability about 150 years in the future that Bennu may in fact impact our planet, creating a natural disaster. So OSIRIS-REx is really trying to study Bennu's orbit very precisely. We know that sunlight actually influences the trajectory of these small asteroids, and we're studying that phenomena, how it interacts with the asteroid surface, and ultimately how it's going to allow us to assess the impact risk that Bennu poses to the Earth.
Absolutely. So the idea of planetary defense isn't just an intellectual exercise. It's something that NASA takes very seriously. A little later in the broadcast, we're going to talk with some people more about protecting the planet from surprise visitors from space. So back to Bennu. We have a lot of exciting stuff to share with you about this tag operation, from how it works to why this overall mission matters so much. And you can be part of this too by joining us on our social media platforms. I'd like to introduce James Traley at our social media desk. James.
Yeah, thanks, Michelle. My name is James Traley, and I'm a producer at NASA Goddard Space Flight Center. And today, I'm joining you on social media to share the excitement of the OSIRIS-REx mission and this incredible sample collection event at Asteroid Bennu. To join us today, you can use the hashtag #ToBennu&Back on Instagram, Facebook, and Twitter to join the conversation and share the excitement with all of us here. You can also follow the mission's Twitter account at OSIRIS-REx for live updates as we make our tag attempt. We actually have a poll going on at this Twitter right now, where we're asking you, how much sample do you think OSIRIS-REx will pick up at Bennu today? I'll check back in with you in a little bit for the results, but for now, back to you, Michelle.
Thanks, James. Okay, so right behind me is the MSA, the Mission Support Area for OSIRIS-REx. And today it is filled with very excited people, the scientists, engineers, and technical specialists who've worked on this mission, in some cases, for more than a decade. So back there is Gary Napier from Lockheed Martin. He's right in the middle of it all. So Gary, what's the feeling in the room?
Michelle, like you said, I am just right behind you, about 20 feet. We're here in the larger Lockheed Martin Mission Support Area, where we're operating 6 of NASA's spacecraft around the solar system, 4 of them at Mars, 1 of them at Jupiter, and this one right here, OSIRIS-REx. We're going to take you into the operations center here at OSIRIS-REx. This is where the flight team is right now. The controllers are already on board. We've heard some good call-outs right now. And in a little while, we're going to come in here and talk to some of them and see how things are going. It's looking really good right now. Back to you, Michelle.
Thanks, Gary. So I think right now we have to acknowledge something, that this is a bit of an unusual broadcast. We're dealing with some pretty big challenges tonight because we're doing this all in the midst of a pandemic. So you'll notice that I'm wearing a mask. I've certainly never hosted an event wearing a mask before. Forgive me if I struggled with it a little bit tonight. Make sure that it's in the right position. And when we interview people, you'll notice that we'll be standing farther away than normal. And also, I'm going to stay right here. Normally I might be back in the mission support area, but I'm not allowed to go back there. I'm isolated from them. So it's amazing that with the incredible operation going on at Bennu tonight, and the people all around me who've been working on this for years to make this a success, we still have to deal with the challenges of COVID-19. And so, tonight our attention is going to be on this wonderful event, actually sampling an asteroid. And, that's incredibly adventurous, it's very happy, but we're going to remember to actually take care of each other. We can't forget that. So please bear with us today as we are working with our masks and trying to do this the best way we can. Okay, so Dante, give us a chance now, give us sort of an idea about how the engineers back there are actually flying OSIRIS-REx.
So it's important to understand that the spacecraft is actually literally on the other side of the solar system, over 200 million miles away from the Earth. So any signal that we were to transmit here would take over 18.5 minutes to reach the spacecraft. So when we get these signals back, we're actually seeing things that happened in the past at the asteroid. As a result, we have to have a very smart spacecraft. It has to make its own guidance calculations and make its own decisions. And in fact, instead of getting high data back, we're only getting a very low data rate, what we call breadcrumbs, just key pieces of information from the spacecraft that tell us when key events have taken place in the tag sequence.
OREX has processed its next image. Position uncertainty is 0.9 meters.
So that's an example of the kind of information that we're getting back from the spacecraft. It's got its onboard natural feature tracking system, which we're going to hear a lot more about today.
Absolutely, yeah. All right, so I guess after that, we are dealing with, actually the tag event itself, but I understand that we're not going to be able to see images tonight in real time, that we have to wait a while. Why is that?
The images take a lot of data to bring back to the bring back from the spacecraft to the Earth. And since we're on that low data rate, what we're using today is this real-time simulation that we've put together. So what we're seeing here, and we'll be referring to this throughout the broadcast tonight, this isn't any kind of real information from outer space. This is what we expect the spacecraft to be doing. So it'll let us know when key events are programmed to take place on the spacecraft and to be received back on Earth. There may be some lags in communication, but this is going to really help us visualize what's actually happening at asteroid Bennu.
So when will we expect those first images?
So everything's going to play out at this very low data rate through most of the broadcast today, and then the spacecraft has to back away from the asteroid surface, it has to cool off, it has to get back on its solar arrays, and then it's going to turn that high-gain antenna to the Earth this evening, and we expect images to be coming in overnight, and we hope to have some great information for everybody by tomorrow.
I'm really looking forward to those images. People around the world are. So at this point, the spacecraft has left its home orbit, and it's on its way to the sample site. And every minute now, we're drawing near to that moment when OSIRIS-REx touches the surface of Bennu. So while we're waiting, let's check in with James at our social media desk.
Yeah, thanks, Michelle. So a few days ago, we actually hosted a Reddit AMA with a few of our scientists and got a lot of fantastic questions. We wanted to recap a couple of them for you right now. So our first question asks, how is it possible to map such a tiny speckle in the sky? Do you have any detailed images that you can share? Do you really see the landing site, or is it all based on measurements of some weird properties and calculations? So yes, our first observation of Bennu actually came from right here on Earth, from the Arecibo Observatory in Puerto Rico. This huge radio telescope gave us a basic understanding of the rough shape of Bennu, this kind of strange top-like shape that you see right here. As OSIRIS-REx was actually out in space and began making its approach closer and closer to the asteroid, it used its suite of onboard camera instruments to actually image the surface in increasing detail. Bennu grew in detail from just a few tiny pixels on our screen to this super high-resolution world that you see right here, littered with giant, rugged boulders. Another question from Reddit is asking us, let's see here, as it loads in, yes. So, would it have been feasible to have a robotic arm pick up a rock? Would a single rock have been better than 100 tiny grains of sand or ice? So the team had originally designed OSIRIS-REx to sample on a nice, flat, sandy-like surface. But as you just saw, Bennu is not at all like that. It's super rugged and filled with giant boulders. So the team had to work with what we had designed for, which was that flat, sandy surface. If we were to try to sample on a rock, that actually presents a number of challenges of its own. For example, if we were to pick up a rock, it might actually just crumble away, and we wouldn't actually get a sample out of it. Also, some of these rocks might actually be a bit too stuck to the surface. And if we were to try to pry those loose, they might not actually budge, and we wouldn't actually even get a sample. So, these are all things that the team has to consider when designing something that's going to be operating millions upon millions of miles away from us here on Earth. So for now, back to you, Michelle.
Thanks, James. We'll be back to you more for later. Okay, now, I have been a Star Wars fan nearly all my life, and in one movie, Darth Vader said, rather famously, that asteroids do not concern me. But that is certainly not true for us this evening. We are all about asteroids here at the Mission Support Area in Littleton, Colorado. And we are bringing you live coverage of our attempt to collect a sample from the asteroid Bennu. Now, OSIRIS-REx is a one-of-a-kind spacecraft with an extraordinary team of engineers and scientists charting unexplored places. It was launched on September 8th, 2016. The vehicle has traveled over 2.2 billion miles on a complex route to reach Bennu. It's scheduled to deliver its precious cargo back to Earth in 2023. So now let's take a closer look at OSIRIS-REx.
Over 200 million miles away from Earth, NASA's OSIRIS-REx spacecraft is preparing for an ambitious sample collection attempt at asteroid Bennu. Before it makes its approach to the rocky surface, let's take a look back at some of the incredible firsts for this mission, which almost seem like something out of a Hollywood movie. This is the first asteroid sample return mission for NASA, and it could be the largest return from space since the Apollo astronauts brought moon samples back to Earth. While getting set to grab a sample, OSIRIS-REx has set not one, but 2 Guinness World Records. Its first for the smallest ever body orbited, and its second for the closest orbit of a spacecraft. This tight orbit has brought the spacecraft so close to Bennu that OSIRIS-REx's onboard cameras and laser altimeter have been able to image and characterize the asteroid's surface and shape better than Earth, our own moon, or any other celestial body. OSIRIS-REx has imaged Bennu down to 5 cm per pixel resolution, providing us with an unprecedented view into this rocky and boulder-filled world. With 28 onboard thrusters, OSIRIS-REx is one of the most maneuverable spacecrafts. This allows it to carefully and precisely descend to a spot on Bennu that is no larger than a few parking spaces. There have certainly been some unexpected twists along the way. However, OSIRIS-REx has capitalized on these moments. Right after arriving at the asteroid, OSIRIS-REx imaged rocky ejecta that has been bursting off Bennu. This is the first time we have been able to observe the entire life cycle of a natural satellite ejecting off an object, entering into orbit, and returning back to the surface. Because of Bennu's extremely rocky surface, the team needed to adapt the spacecraft's navigation method to an optical approach known as natural feature tracking, or NFT. This is the first time this approach has been used in space, and it will allow OSIRIS-REx to steer itself down to collect a sample from Bennu. And now, OSIRIS-REx is looking to set another first for NASA. Successfully collect a sample of an asteroid and deliver it to Earth by 2023.
Welcome back. If you're just joining us, I'm Michelle Fowler from NASA's Goddard Space Flight Center, and with me is Dante Loretta from the University of Arizona. And you are here with us on a historic evening. It will be NASA's first sample return from an asteroid, the attempt to actually sample the asteroid Bennu. The spacecraft OSIRIS-REx is descending toward Bennu right now to take a sample and return it back to Earth. So Dante, let's talk more about this real-time simulation that we're looking at.
Yeah, it's been an exciting day already, Michelle. We're well over 3 hours into the TAG sequence, which is the pre-programmed set of commands that are already on the spacecraft. Earlier, we departed our orbit around the asteroid, so we're flying over the sunlit side of the asteroid, taking images for the onboard guidance system called natural feature tracking. A couple other key events that have taken place already is the spacecraft has deployed its robotic TAGSAM sampling arm, so the arm is ready, in position to collect that sample. And we've turned on and started collecting science data from one of our science instruments, the Otis Thermal Emission Spectrometer. The spacecraft has already moved into its second natural feature tracking attitude and is getting onboard positional updates as we speak. And I can tell you, everything is going exactly according to plan right now. It looks really good.
Oh, it's been an exciting day. So OSIRIS-REx has traveled more than 2.5 years as it navigated its way to this delicate orbit around Bennu. And once there, it began mapping the surface, one of the many tasks it and the engineering team have been conducting since it arrived. And there have been some challenges and surprises too, correct?
Absolutely. I can tell you already the science return from OSIRIS-REx has been phenomenal and rewritten a lot of things about what we know about asteroids. I'm going to talk really about 3 of some of the most interesting results for me. First off, we learned literally about 1 week after getting into orbit that Bennu is what we call an active asteroid. It is ejecting particles from its surface. These particles are coming off at relatively low velocities for the most part. They're actually going into orbit, spiraling around the asteroid, providing some excellent science, allowing us to map out the gravity field of this small body at an unprecedented detail, way beyond what we expected to do. The other thing that we saw right away as we were approaching is that there was some generally dark black surface as expected, but there were these really bright boulders that were shining like beacons to us. And as we trained our science instruments on there and characterized their mineralogy, we were actually able to link them to another asteroid called Vesta, one of the largest asteroids in the solar system, and actually the target of NASA's Dawn spacecraft, which did a phenomenal job characterizing this target. And this just shows you that these asteroids are exchanging pieces back and forth as they collide into each other and shoot their particles off into space.
OREX has processed its next image. Position uncertainty is 0.6 meters.
Wow. And I would say, back to the science, the final result that really is important from this mission is we did expect this asteroid to look sandy and beach-like. And that was based on the thermal properties as determined from telescopic observations from Earth. And we got there, and we used the Otis and our OVIR spectrometer to map and produce a thermal inertia characterization of the entire surface. And everything turned itself upside down based on our models. The areas that we thought would be beach-like based on thermal properties turned out to be the largest boulders on the asteroid's surface. And the more fine-grained regions turned out to have what we call this higher thermal inertia, completely opposite of everything we expected, propagating a lot of great science as a result.
And so when you mentioned that there are these bright rocks from Vesta, does that means that Bennu was once in the asteroid belt between Mars and Jupiter?
That's right. Bennu is currently a near-Earth asteroid, but it's a recent wanderer into the inner solar system. We actually think it's fragments of a much larger asteroid that was catastrophically disrupted maybe 1 billion years ago.
Wow, that is so cool. Thank you so much. Okay, now as challenging as it is actually getting to Bennu, capturing a sample of the asteroid is something else entirely. And the team needed to develop this remarkable system. The OSIRIS-REx mission has been in development for almost 20 years, with the engineers and scientists developing new technologies and strategies to accomplish something that's honestly never been done before. And this is particularly challenging because Bennu has such a weak gravity field. So when you think about going into orbit around something, how do you orbit something where the gravity can't grab you and actually push you into orbit? It's all about flying the spacecraft. It's also very difficult to take a sample in a very low gravity environment. So thankfully, we have the mastermind behind the device that's going to take the sample tonight, Lockheed Martin's Bo Bierhaus. Welcome, Bo.
Thank you, Michelle. It's great to be here.
Okay, so let's talk a bit about why working in this low gravity environment makes it tough to get a sample, because you might think sort of at first you could just take like a robotic claw or a robotic arm and scoop something up, but that's not going to work in these conditions.
That's exactly right. The microgravity of Bennu provides a challenge of sampling that we don't normally face on Earth. You can imagine trying to use a shovel or a scoop on Earth, and the ground pushes against you, but the gravity keeps you on the ground. On Bennu, the surface gravity is thousands of times lower than on Earth, so if you pushed a shovel or a scoop into the ground, you'd push yourself right off the surface. So we had to come up with a technique that worked within this very low gravity. We also had the challenge of uncertainty of the mechanical properties of the surface. And both of those things made landing a challenge. We wouldn't know how to grapple particularly well in this material. So we had to come up with a technique that worked in the microgravity environment and that could work in this tag architecture, this touch-and-go architecture of just a few seconds long.
Now, I understand you have brought some models with you, both of the spacecraft and of the instrument that will be taking the samples. So show us what you've got here.
That's exactly right. So this is a scale model of the spacecraft. The arm is extended in the sampling position. Partway down the arm, you can see 3 gas bottles. We'll use one of them today. This has high pressure nitrogen gas, which passes down the arm into the TAGSAM head itself. And here I have actually a full-scale TAGSAM. It's actually a device that we used for collection testing on Earth. The gas comes down. I don't have the tubing here to show you, but the gas comes down to the center of the TAGSAM, is split into 2, and passes underneath the head. There is now a high-pressure bubble of gas underneath the head that is mobilizing material, much like wind blows dirt on a dusty day on the Earth. And we're surrounded by the vacuum of space. So the gas there's a high-pressure gas underneath TAGSAM, and it will escape into the low-pressure environment of the vacuum of space surrounding it. And it does so through this screen around the entire perimeter of the TAGSAM head itself. But while the gas can escape, the screen traps the material safely inside.
It's one of these sort of brilliant things about engineering for space is to have things that are really, really rigorously built and they can't break easily. And so there aren't even any moving parts here, and you're using the vacuum of space itself to provide the pressure to collect the sample.
That's exactly right. When we were first designing this device many years ago, we were thinking we wanted to keep it as simple and as robust and as foolproof as possible. We didn't want any mechanisms, we didn't want any electrical devices. The entire collection is driven by the dynamics of the gas itself. So once the gas is released from the bottle and travels down the arm, the gas does all the work.
That's so cool. So what size particles are we talking about collecting here?
Well, TAGSAM is designed to collect 2-centimeter particles, and I have some examples here to show you. So this is a 2-centimeter sphere. It's about the same diameter as a nickel. But of course, most geologic materials aren't actually perfect spheres. Most geologic materials are irregularly shaped.
OREX has processed its next image. Position uncertainty is 0.5 meters.
Oh, that is fantastic. Excellent. So we're going where we need to go to get this material. So most geologic material is irregularly shaped. So this rock is actually about 4 centimeters long in its longest dimension, but we were still able to collect this in a test on Earth. And that's because even though it's 4 centimeters in this dimension, you can see that it's much less than 2 centimeters in that dimension or even 2 centimeters in the other dimension. So while we're limited in one direction for 2 centimeters, as long as the other 2 directions are less, we can actually collect much larger particles into the TAGSAM head itself.
Well, excellent. So I understand we have some animations queued up to give us a sense of what's going to happen on the asteroid tonight.
Sure thing. So what you're seeing is the spacecraft descending at a leisurely 10 centimeters per second to the surface, 15 times slower than walking speed. It contacts, the spacecraft senses contact and fires the gas. The gas mobilizes material underneath the TAGSAM head. That gas escapes into the vacuum of space through the perimeter, and materials collected inside the TAGSAM head. The spacecraft fires its thrusters and backs safely away from the surface of the asteroid.
Well, thank you for the tutorial, Bo. I mean, clearly the science community is going to be very excited to study whatever TAGSAM collects. So thank you so much.
Thank you. It's wonderful to be here.
Okay, well, speaking of all the important the thing that's happening in less than an hour, right now, before we get any later, it would be a good time for us to get a tour of the NERV Center here at Lockheed Martin Space in Littleton, Colorado. Right behind me is the Mission Support Area, or MSA, and that's where OSIRIS-REx team members are keeping an eye on the spacecraft right now. So let's send it over to Gary. What's going on, Gary?
So as I showed you earlier, we're just around the corner from you. This is the heart of the TAG operations, and we thought this would actually be a really good time to kind of check in with the team, see how things are going, and the best person to do that is joining me, and this is Sandy Friend. She's the OSIRIS-REx Operations Manager here at Lockheed Martin. So, Sandy, thanks for joining us. How's the team doing?
Oh, the team is great. We've been here on console since 6 o'clock this morning, sending the final commands, getting ready for TAG.
Really cool. I know there's like 40 people on your overall flight team, but it seems like there's about 20 of them here right now. Maybe kind of give us a little idea of who some of these folks are and what they're doing.
Yeah, absolutely. So this is the amazing OREX team. You can see all of our subsystems here on console, monitoring their telemetry. Like you mentioned, we can't have everybody in here. We do have many team members supporting from other conference rooms in the building and some even from home. So let's talk about a couple of the positions we have in the room. In the back corner over there is Dale Howell. Dale is our TAG phase lead. You've been hearing his voice calling out events as they complete on board the spacecraft. Here in the center area, we have Curtis Miller. Curtis is our NFT lead. He is watching natural feature tracking, and that is how we are navigating to the surface of Bennu today. So he is watching how NFT is performing, how many features we're matching, and how that system is working.
So I know natural feature tracking, like you're saying, is kind of keeping an eye on telling us where we're going. And I know we're going to get into that a little bit later in the show. But also it's important just to stay in communications with the spacecraft. So what about comms?
Yeah, absolutely. So right behind me here is Sierra Gonzalez. She's our real-time operator, or our ACE. She is working with our Deep Space Network partners. Currently we're on a station in Goldstone and in Canberra, making sure we maintain our comm link. And our comm link is only 40 bits per second, so we're just bringing down that key information, but Sierra's here to make sure we keep that link going and our station operators informed. And right next to her is Estelle Church, and Estelle is our systems coordinator for this event. She's built all the command products that are executing. She's keeping an eye on how everything is progressing on board the spacecraft, talking to all of our subsystems here in the room, and making sure things are going just as planned.
Very good. I know you yourself have actually been on this project for quite a while, even back to development. I mean, how are you feeling tonight?
No, actually, I'm excited. I feel like we've done everything we can to make this successful, and I've been on this mission for 7 years, so I've watched it go from a spacecraft on paper to being built in our high bay to launch and everything here. And yeah, I'm excited. My kids were excited this morning, and we are ready.
Right on. That's so fantastic. So we're going to let you guys get back to it. I know we don't want to interrupt too much. Sandy, thank you so much for joining us. And I know that folks around the world are paying attention to this right now. We're seeing a ton of social media coming in. So let's go over to James on the social media desk and see what some of those conversations are about.
Yeah, thanks, Gary. It's awesome to see the team over there in the MSA. You can really feel the energy in the room, especially after every call out from Dale. And right on cue.
is slewing to the TAG attitude, the third and final natural feature tracking attitude.
All right, so we're inching ever so closer down to the surface of Bennu. But today we also want to hear from you. So you can check in on live updates at our Twitter account at OSIRIS-REx, or using that hashtag to Bennu and back across social media to get in on the conversation. In the meantime, a question I had when I first started covering the mission is, how do you even begin to prepare for a mission of this scale? I mean, when I first heard about OSIRIS-REx, it really seemed like something out of a big budget movie. But this is a reality. We're actually going to be trying to sample on an asteroid. To put things into perspective for you, Bennu is about the size of the Empire State Building. That's really small for an object and makes it exceptionally challenging for us to orbit something with such a weak gravity field. And that sample site we're going for today, Nightingale, it's just a few meters in width, which is about the size of a few parking spaces. So just take a step back for a second and put yourself in the shoes of some of those engineers on this mission. And imagine trying to park a spacecraft on an asteroid 200 million miles away in a space no larger than a few parking spots. As if parallel parking on an asteroid isn't hard enough, imagine also trying to dodge hazards like rocky boulders and all kinds of things as you're making your descent down to collect a sample. And on top of that, the team has actually programmed the spacecraft to steer itself down to the surface. It's truly incredible, this mission, and all the foresight that went into it. It really blows my mind. We actually have a couple questions coming in from Twitter, and a lot of people are actually asking about our fuel usage for the mission. This one question is asking, how does the craft have enough fuel to return back to Earth from the asteroid? So we're looking to bring that sample back in 2023, and OSIRIS-REx's thrusters are actually powered by hydrazine, which is stored in a container on the spacecraft. We're tapping into a little bit of that fuel today, on the order of maybe tens of grams, not a lot, because as you remember, Bennu has this microgravity environment, and it just requires a little bit of thrust to kick us in the right direction to collect a sample. That return trip back to Earth, that's a bit of a different story. We're going to be using a lot more fuel for that. But don't worry, the team has thought way ahead and has packed more than enough fuel to get us back here safely in 2023. But there's a lot more to come, and I'll check back in with you in just a minute. Back to you, Michelle.
Thank you, James. Okay, so let's take a quick look at the simulation to see where we are. As you notice with the simulation, the spacecraft has its arm extended now, and is on a slow path toward the surface. So as we get closer to the moment of contact, the drama starts to happen in slow motion. And this is to maximize precision and minimize unintentional surprises. So, speaking of surprises, there is one big aspect of the OSIRIS-REx mission that's all about preparing for the unexpected. And joining us to discuss this is NASA Planetary Science Division Director, Lori Glaze. Now, Lori, you have kind of a dramatic specialty and a responsibility that comes with your position at NASA. You actually worry about things like planetary protection.
Yes. Planetary protection or planetary defense is sometimes what we call it, defending our planet from potential impacts. And Bennu is in a special class, and I think Dante spoke about this a little earlier, that Bennu is actually a near-Earth object, or a NEO. And a NEO, or near-Earth object, is an asteroid or a comet that orbits the sun, much like our planets do, but they're slightly unusual.
OREX has reached the third and final natural feature tracking attitude. The spacecraft will hold this fixed attitude until tag.
Excellent. Great news. So back to NEOs.
Yes.
So NEOs are somewhat unusual in that their orbits bring them within the vicinity of Earth's orbit. The technical definition of a NEO is something that comes within about 30 million miles of Earth's orbit. And asteroids actually come close to the Earth all the time. 1 or 2 per week actually pass in between the Earth and the Moon. But most of those are really small and not dangerous. But asteroids of a much bigger size that could actually do damage to the Earth's surface if they were to impact, they can pass by Earth closer than the Moon about once per month. And that's why it's really important for us to find them as early as possible so we can track their orbits, study their characteristics, and if necessary, we can mitigate a potential future impact threat. And that's where a mission that we're building now called the Double Asteroid Redirection Test, that's where DART comes in. And DART is going to launch in next summer, 2021, and it's going to test something we call the kinetic impactor technique. That could be used one day to help us mitigate a future potential impact threat by bumping an asteroid ever so slightly that's on a collision course with our planet into a slightly different orbit so it misses Earth.
Just a little bit is all you need.
Just a tiny bit.
So, I mean, that is really exciting. Now, I also understand that not all of the asteroids in the solar system are the same. There are different sorts, and NASA has some upcoming missions to study these different kinds of asteroids. So tell us a bit more about that, please.
Absolutely. Yeah, we know that the majority of our asteroids are found in the main asteroid belt between Mars and Jupiter. And in fact, we have a mission that's going to launch in 2022. It's called Psyche. It's going to visit one of the biggest asteroids in the asteroid belt that's actually called 16 Psyche. And this mission is going to arrive in early 2026 and help us better understand if this asteroid is potentially actually the core of a planet-sized object. We also have other types of asteroids called Trojans that are clustered in two groups that lead and trail in Jupiter's orbit due to a balancing act of the pull of both Jupiter's and the Sun's gravity on them. NASA has a mission to those Trojan asteroids called Lucy. It's going to launch next fall, about a year from now, and it's going to go visit several of these Trojan asteroids. We have a new mission called Janus, and we selected this mission through our Simplex small mission program line. This mission is going to send actually two small spacecraft, very small spacecraft, to two binary asteroid systems and help us understand what it is that makes these binary asteroid systems different from one another. And so studying this full breadth of these diverse small worlds will continue to help us fill up the knowledge gaps of how our solar system actually formed and evolved over time.
So it seems with all these missions coming up, we're sort of in a golden age of asteroid exploration. But then there's this other aspect of the OSIRIS-REx mission, which is the sample return. And it turns out that we're also beginning this golden age of sample return to it, and not just to asteroids.
You're absolutely right. And we're really excited about all of these samples because they're so precious and there's so much science we can do with them. In addition to OSIRIS-REx, we're also partnering with the Japanese Space Agency on their mission called Hayabusa 2, which is actually already on its way back, bringing a sample from Ryugu. They're going to be coming back to Earth in December. We're also partnering with Japanese Space Agency on another mission of theirs that's going to return a sample from Phobos, which is one of the two moons of Mars. And then finally, at the end of this decade, we're going to send a mission to Mars to retrieve the samples that are collected by the Perseverance rover, which is really truly our first astrobiology mission from NASA. And it's focused on looking for finding potential life, ancient life on Mars. So sample of return is really important because it allows us to study these pristine samples back here on Earth. We can then take advantage of our room-sized laboratories. All of this.
OREX ops. OREX has begun moving the solar arrays to the Y-wing configuration to avoid possible contact with the surface during tag.
Great news. Moving right along. So when we bring the samples back, this allows us to use all of the laboratory capabilities that we have here on Earth. We can use the full suite of the scientific instruments that we have at our disposal to help us better understand the sample, their compositions, and the history of the body from which they came. And also having the samples back here on Earth allows us to preserve them for future generations to come and allows our future explorers to analyze the samples using techniques and instruments that haven't been invented and to ask questions that we don't even know to ask yet.
That is just so cool. I mean, your life is all about how we navigate unknowns. This is something that's happening in real time around us tonight. So it's reassuring to know that there's an organized plan that you're in charge of to help take some of the uncertainties out of at least one dramatic category. So Lori Glaze, thank you for joining us this evening. So good to see you.
Thank you so much for having me. I just want to add that it's been fantastic to watch the OSIRIS-REx mission so far, and I'm really, really excited for what's ahead tonight, and I want to say congratulations to the entire team.
Thank you so much.
Thank you.
Now, asteroids are not easily navigated. They're hard to see, they have low gravity fields, they're dark and rocky, and traveling around the solar system where everything is moving rarely means traveling in a straight line. Let's take a look at some of the big challenges the team has faced to get to this point.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional close passes over the asteroid and rethink our entire plan for grabbing the sample. After the additional observations of Bennu, we had to down-select to 4 sites, and then go back and survey those sites even further to select the final primary sample site.
My first impression of Nightingale is that's the last place I wanted to go. But as we started looking at other sites, we saw that 1, this is probably one of the most sampleable sites, and 2, we were overperforming in our navigation capability and our ability to contact. Natural feature tracking works a lot like the human mind in that we pick up landmarks along the way. As we descend, we look at features on the ground. We program the computer to recognize certain features. It takes a picture, says this feature is not where I expected it to be, it's a little bit off to the side, updates its position based on where it's pointed and where that feature shows up in the camera position.
The tag event is our touch and go event, which is where we'll actually be retrieving the sample from asteroid Bennu. We start with a series of maneuvers, one of them being the checkpoint burn, which is where we'll actually check our position velocity in relation to the sample site.
And then the match point burn, about 10 minutes later, will zero out our horizontal velocity relative to the surface. And then about 10 minutes after that, we make contact with the tag SAM, fire the gas bottle, and then back away.
And we hope to get at least 60 grams of sample, and then we'll be able to store that and bring it back down to Earth.
But there are several things that could go wrong, and we also have to be prepared that we won't be successful on our first try at Nightingale.
We don't only get one shot at tag. We actually have 3 nitrogen bottles on board the spacecraft, so we can potentially do 3 tag attempts if needed. We go through several what-if scenarios, and this is how we actually prepare for a lot of our contingencies.
So we've had to look all around the surface and identify the rocks and boulders that if the spacecraft were to tip over up to 25 degrees, it could come into contact and be damaged.
We had to develop a hazard map, which we program into the computer and says, if you're getting too close to those hazards, we'll do a wave off, we'll back away from the asteroid, and we'll come back and do this another day.
Everything might work perfectly. We come down, we touch the surface just where we want to, we fire the gas bottle, but the area we contact is covered in large rocks. Those rocks would prevent any fine-grained material from being stirred up and captured in the tag SAM head. Another similar scenario is if the tag SAM were to touch on the edge of a boulder and become tipped up. In that case, when the gas bottle fires, much of that gas escapes out the side, not churning up the material that we want to capture. The day of tag is going to be really exciting, but the excitement for our team doesn't end there.
We have to verify that we have a proper sample.
First, we're going to image the tag SAM head by sticking it in front of one of the cameras. Then we're going to do a maneuver called the sample mass measurement, in which we stick out the arm and we spin the spacecraft in order for us to decide if we've collected enough mass to be able to stow the sample and return home, or if we have to try again.
This is the culmination of a lot of work. It's probably one of the most exciting missions that I've worked on.
It is really exciting to know that we're finally going to be able to touch the surface of the asteroid and collect the sample to return back to Earth.
So step back for a moment and realize that tonight's events are exceedingly rare and historic. Humanity has only landed on a few different bodies in the solar system, and actually retrieving a sample is even more rare. So luckily with me tonight are some of the people that know better than anybody all the challenges that it took to get here. So let me introduce Mike Moreau. Mike is the OSIRIS-REx Deputy Project Manager at the Goddard Space Flight Center, and Coralie Adam is Tag Navigation Manager at Kinetics Aerospace. So welcome, Mike and Coralie. How you guys doing?
So excited.
So excited. We're less than a half hour from tag now.
Yeah, you can feel the energy all building. So I should mention at this point that it's possible, you've been hearing this before, cheers from the MSA. So can you give us a sense of what's going on right now?
Yeah, so every few minutes, a navigation camera image is taken by the spacecraft of the surface below, and it's sent to the Natural Feature Tracking System. And that system identifies features in the image and sends a signal back to Earth that it was successful.
Position uncertainty is 0.5 meters.
And the team celebrates. It tells us we're on track to our next target and on track to tag.
Absolutely. So now, clearly there's a lot to talk about in terms of the mission, but once again, you had to do all of this in the midst of this COVID-19 pandemic. So were there any mission expectations that changed? How did you deal with that?
Yeah, for sure. I mean, as the whole world was coming to grips with the pandemic in the March timeframe, this team was in the midst of preparing for our first TAG rehearsal, the checkpoint rehearsal that would take the spacecraft only 65 meters above the surface. So we had to rethink the entire way in which we were going to do that rehearsal with only a skeleton crew here in the building and with many of our team members remote, as Sandy mentioned before. Today we have people literally all over the building monitoring, also at Goddard Space Flight Center and at the University of Arizona watching this event today. But thankfully we got through checkpoint rehearsal in April and match point rehearsal in August.
And all those special considerations, they're still going on around us today, right?
Yeah, I mean, you could see people spaced out in the MSA when you were over there. And, you know, we had more time to prepare for TAG in order to accommodate that and get everyone into the building here today. So I'm just incredibly proud of our team for, you know, their efforts to keep the project on track for TAG in spite of all of these challenges.
Absolutely. So I know NASA's famous for having to deal with unexpected situations, and this COVID-19 thing is kind of a different flavor of unexpected situations. So we're going to deal about that. Okay, so now let's talk more about the challenges of TAG that we introduced in the video segment. So Corley.
Right, so you've seen that Nightingale site is an extremely challenging spot to navigate into. There's boulders all around it. This is totally different than how we originally designed the system to target a 50-meter diameter area. Nightingale is 10 times smaller than that. So it required the whole team to rethink how to safely navigate into the contact with the surface, and we had to come up with some new ideas.
Yeah, so the original navigation approach used LiDAR, or laser-based navigation, to take us to the Nightingale crater. But when we saw what Bennu looked like, we realized we had to switch to a vision-based approach, and that's the NFT system that you've been hearing about.
Yeah, so the Kinetics navigation team has spent the last 2 years learning how to navigate around Bennu using optical navigation techniques very similar to what NFT is doing on board the spacecraft today. So Kinetics worked with scientists and the Lockheed Martin NFT team to map the surface of Bennu.
OREX has processed its next image. Position uncertainty is 0.5 meters.
Really honing in. So we mapped the surface of Bennu to unprecedented resolution of 2 centimeters per pixel, which is better than what we've done on our own Earth and Moon. So it was a huge Herculean effort to get to this point where we're comfortable handing the maps and the keys over to the spacecraft to get us down into this small site today.
Absolutely. So I guess right now it's time to say goodbye to you guys. The best of luck for today. I'm really excited, and it's great to be with you guys.
Thank you, Michelle.
Yeah. So right now, I think probably the best thing to do is to check in with Gary Napier. I guess we're going to go back and see how things are going back there. So to Gary.
So things are going really good right now, Michelle. We're actually going to talk to Heather Enos here, the Deputy Principal Investigator for the OSIRIS-REx mission out of the University of Arizona. Thanks for joining us, Heather.
Hi, Gary.
So what's really interesting, Heather, is that you actually feel that, long missions like this are really important. I mean, you go from design to build, but operations is really quite a while. That it's actually really important to involve that next generation and kind of bring that generation up, correct? Talk to us a little bit about that.
Absolutely, Gary, you're right. All the way back from when we started planning this mission, OSIRIS-REx, we recognized it's a long duration mission. And although that presents challenges for retaining your key personnel, we actually took it as an opportunity to use this mission to train our next generation of students and science engineers and scientists. A good example is we had one of our science instruments is called REXUS. It's an X-ray spectrometer built by a team of students at MIT and Harvard. So real hands-on.
That's really interesting. I mean, I understand you also have some folks that actually were students and came onto the team later?
Yeah, so being at the University of Arizona on a PI-led mission, we have had hundreds of undergraduate and graduate students working on this mission over the course of the last decade. And 2 of our students that started off as students are actually 2 of our navigation team members. That's Dan Wibben and Eric Sarr.
Wow, so they're on console.
They're on console right now. Yeah, they are.
At this time, NFC has computed the checkpoint and match point burn updates to correct for errors in the trajectory accumulated since orbit departure. Checkpoint burn in 2 minutes.
So checkpoint turn in 2 minutes. We're going to throw it back over to Michelle, because I know this is an important update for her. So, Michelle, thanks. Back over to you.
Thanks, Gary.
Well, absolutely. So, Dante, tell us what this important milestone checkpoint means.
This is a really important part of the mission right now. So we've been hearing about natural feature tracking and how it's processing these images.
OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 0.46 meters.
Right, so what it's doing with that information is it's calculating how it's going to fire its thrusters for this checkpoint. When we left orbit, we were on a trajectory that would take us over the surface of the asteroid, and if nothing else happened, we would safely fly past Bennu. Once we fire the thrusters for the checkpoint maneuver, we're actually going to start descending down towards the asteroid surface, so this means we're going to be on our way to make contact. So natural feature tracking has been doing nothing but calculating this maneuver since we started taking images.
So this is one of the big deals. This is one of the big milestones coming up.
This is huge.
Yeah.
Absolutely.
I know that as we look at the simulation, there's an interesting configuration the spacecraft is in. Oh, I see the thrusters firing.
That's right. You can see we would expect right now on the spacecraft the thrusters to be firing, so we're going to be paying close attention to Dale Howell to let us know we've gotten telemetry back to telling us that maneuver has succeeded.
In the meantime, if you want to tell us a bit about the configuration it's in, go ahead.
Yeah, we heard Dale call out earlier that the spacecraft was in the Y-wing configuration. There we just reconfigured the solar arrays to get them up away from the asteroid surface, basically to protect their active areas from any dust loading that might be kicked up during the tag event.
It's another excellent Star Wars reference.
That's right, always. You can also see here in the simulation the Nightingale sample site, now down in the lower corner here. This is our target. This is what we're trying to get into with that spacecraft. So.
Now, it looks like there's a lot of boulders around that.
Yeah, as we've said, generally the surface of Bennu is rough and rugged and covered with boulders. Nightingale really does stand out as a pretty unique, interesting area on the surface.
How you doing?
Doing pretty good. Paying close attention to that call out, waiting for Dale to tell us that checkpoint has occurred.
Absolutely. So what we're waiting for right now is the call out that checkpoint has occurred, and the OSIRIS-REx spacecraft has begun its descent towards the asteroid surface.
Right. Any time now.
And it's probably worth mentioning.
OREX MSA on OREX Ops. Checkpoint burn has completed.
Okay, we're heading down towards the asteroid surface at this point.
Oh, wow. Oh, wow. Okay, well, you know, I guess the next thing that comes up is going to be this match point maneuver. So that's the next big milestone for us.
That's right. So we've got one more firing of thrusters with the spacecraft to get us lined up for the sample acquisition event. We call that the match point because what we're doing there currently as we're flying over the asteroid surface, in fact, it's the asteroid surface that's rotating underneath us. Mm-hmm. And when we fire thrusters for match point, we're doing that to match that rotational velocity so that the spacecraft becomes station keeping essentially over that Nightingale sample site.
Mm-hmm, absolutely. All right, so I think we have a little bit time now to turn to our social media desk. So James, what's going on in social media?
Yeah, Michelle, it's super exciting. You just heard that checkpoint burn confirmed. We are now just very, very close down to the surface of Nightingale. And you guys have been really excited over on social media too at that hashtag to Bennu and back. Lots of great messages rolling in here. Someone's really excited for our little robot friend to go rock hunting on the surface. We had someone who actually attended our launch back in a couple of years ago at Cape Canaveral and are now watching the broadcast live with us today, excited for that sample collection event. We have Philip who kind of puts it in perspective for us here. He says, this is amazing and extremely difficult in so many ways. Bennu's orbit, spin, inclination, the orbital mechanics of this long mission are just astounding. I can only imagine how many orbit simulations have been made here on Earth. It really is a crazy mission, and we also have our animal friends, our pets, cheering us on here as well. Bennu is rough from this couple of our pets here, really excited. So we're now just minutes away from that match point burn, and for that, I'll kick it back to you, Michelle.
Okay, excellent. So, you know, just a few minutes ago, Dante, you were saying that this landing site is sort of a unique area on the asteroid. Tell us about this site.
Yeah, we spent an enormous amount of effort selecting the area on this asteroid surface where we wanted to get the sample from. And we kind of divided our analysis up into 4 different categories. First, we were looking at the deliverability. And this was a real challenge because, as we've seen earlier in the broadcast, the original guidance accuracy was 25-meter radius, and we're trying to get into an area that's 10% of that size. We have solved that problem with our amazing natural feature tracking solution, and as we've heard, that's worked really well, and it has updated its checkpoint and its match point maneuvers on board based on that information. That gets you down to the surface of the asteroid. So the next thing that we have to worry about is maintaining spacecraft safety. There's a lot of hazards on this asteroid surface, things that could damage a critical component, and we decided to focus safety on the things that were needed to get the sample back to the Earth. So there were certain things we could lose at this point in the mission if they didn't fulfill that objective. We still have some upcoming major milestones that help us maintain that spacecraft safety. Now natural feature tracking is going to be switching over to calculating the contact point on the asteroid surface. And it has a piece of software on board called the hazard map. It's actually determining, is the location that I'm going to touch down on safe, a green area on that hazard map, or is it potentially hazardous, a red area on that hazard map? So as we get closer to the asteroid surface, a key moment is the 5-meter crossing. That's when the spacecraft makes that decision. Do I continue down to collect the sample, or do I back away and live to tag another day? After that, you've got down there, your spacecraft is safe. There's got to be something for you to pick up. Earlier in the broadcast, Bo Bierhaus showed us the size of particles that TagSam could actually collect. So we had to map the Nightingale area and other potential sample sites well below that 2-centimeter resolution. And in fact, we got 3.5 millimeters per pixel all over the Nightingale sample site. And we were really excited to see lots of particles of that size. And of course, the final parameter that we were looking at was the scientific value. And I can tell you the good news is any sample from Bennu is scientifically valuable. We've seen these hydrated clay minerals, we've seen organic molecules, carbon-bearing minerals all over the surface of the asteroid, exactly the kind of material that we're hoping to bring home.
So I understand the next big milestone we're looking for here is something called match point.
That's right.
So what happens at match point?
Match point is the final maneuver that the spacecraft performs by firing its thrusters. And that's where we become centered over the Nightingale sample site and begin that final descent down to the asteroid surface. And the spacecraft is solely focused on its safety calculation and the decision on whether or not it's going to proceed down to collect that sample.
Of course, the amazing thing about match point is that the asteroid itself is actually rotating. So when we go to match point, the spacecraft has to match the rotation of the asteroid so it comes directly down onto it.
That's right.
So how fast is Bennu rotating?
Bennu has a rotation period of 4.3 hours. So that's basically the length of the day on the asteroid. On Earth, the rotation period is 24 hours, which is why a day on Earth is 24 hours long. So that translates, because Bennu's a pretty small object, as we've seen, 500 meters or about the same size as the Empire State Building. At the equator, the surface is moving at 10 centimeters per second. And it actually gets slower and slower as you go to higher latitudes. By the time you get to the North Pole, it's 0. Nightingale's pretty far north, so it's actually much lower than 10 centimeters per second. And that just kind of shows you the delicate precision nature of this mission. You know, we've got to get very low thrust maneuvers, very delicate, very slow approach to the asteroid surface. Everything kind of happens in slow motion when you're operating in a microgravity environment like Bennu.
So what's the next critical milestone after match point?
After match point, we're going to be looking for the natural feature tracking system coming back online, taking those images and additional correlations and precision on its knowledge of its position. And we might expect it to actually jump up. We've been hearing natural feature tracking uncertainties on the order of ½ a meter. It may go up a little bit as it goes through.
MSA on OREX Ops. OREX natural feature tracking system has resumed processing. Position uncertainty is 1.6 meters.
So you can see there we went back to 1.6 meters. That's because we went through the checkpoint maneuver. So whenever you impart a thrust like that, it adds uncertainty into the system. And we're seeing that with the natural feature tracking system right now.
That is so exciting. Okay, so we're going to introduce, actually, the Associate Administrator of NASA, Dr. Thomas Zurbuchen. Thomas, thank you for joining us.
So glad to be here with all of you.
It's an exciting time, Thomas.
Happy birthday.
Thank you.
Yesterday,
That's right. Yesterday is his birthday. Yeah, that's right. Happy birthday. So, I guess, everybody here is aiming for this point in time called this TagSam, but it turns out that there have been a lot of friends, a lot of colleagues that have helped get us to this moment. So, who's been along with us on this journey?
Well, look, I mean, there's a number of course, domestic partners, many of them around here. You talk to some of them, but there's also international partners, and the Canadian Space Agency provided the laser altimeter, which is an important instrument here. And of course, we have a partnership with JAXA. What we're going to do is actually share the samples from Ryugu, from Hayabusa 2, with OSIRIS-REx once it's back for maximum science, and that's really what international partnerships are about.
So this is a big mission for NASA, but it turns out that there are many different kinds of partners in a mission like this. Give us a sense of the range of partners that we have.
Well, look, I mean, it starts with the University of Arizona. That's where the leadership is, and with you there and your entire team. But NASA Goddard Space Flight Center is a critical partner with managing, of course, especially also working with Lockheed Martin, who really, with that team deserves a lot of credit, and Kinetics, which was already introduced, as well as many others. If you really look, so often missions like that touch many, many states around the United States.
Absolutely. So, Thomas Zurbuchen, thank you for joining us, and we will see you later on in the program.
How do you feel, man?
I'm pretty excited. This is the final 10, 12 minutes here for contact. I feel really good. The team's in high spirits. As you and I talked about earlier this week, we have done everything possible to make this today a success.
Exactly right. And your mind is already out there, and the spacecraft is already on the way out in real time. Can you imagine that, right?
It's good actually to point out whatever has happened with TAG has already happened. We're well past that 18.5-minute one-way light time.
Absolutely. Hey, congrats. Let's continue doing this.
Yeah, we'll see you later. Thank you, Thomas.
Yep.
Oh, wow. Okay, so we're coming up, I know, on the critical point of match point. So at what point will we know that we really have a sample?
That's a great question. We're not exactly sure what's going to happen right away. We'll know if we made contact with the asteroid surface today. We'll know if the gas bottle fired, and we know that we backed safely away from the asteroid. But we actually have a lot of work to do over the next week or so. We'll take a look at the images that we were acquired during contact with the asteroid surface, and then we'll go into a different imaging campaign. We're about 30 seconds from match point, so we're going to keep our ears open for that critical call out from Dale.
OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 1 meter.
All right, we're back down to a meter positional uncertainty. That's great news. So back to sample verification. We will, after we're well away from the asteroid and everything has kind of settled down, we have that robotic arm. We're actually going to use that to put the TAG SAM head into the field of view of SAMCAM. And we can look not only at the top of the sampler head like we're going to get with the images today, but we can actually turn it around and we can look at the base of TAG SAM. We have, in addition to the gas stimulation, we have contact pads. Simply by making contact with the asteroid surface, we think we can pick up fine-grained particles, less than a millimeter or so. But basically, we're going to be looking for any evidence of asteroid material on or inside the TAG SAM.
Now, obviously, you don't want to go all the way back to
OREX
Earth.
MSA on OREX Ops. Match point burn is complete.
All right. We're heading down. We've got about 10 minutes before contact with the asteroid surface.
Oh, wow. So I was about to say, so obviously you don't want to head back to Earth with not much sample. So how do you know how much sample you actually got?
There's an incredibly clever physics experiment that the team has designed here called the sample mass measurement. So what we're going to do is we're going to place the spacecraft arm out to the side of the spacecraft. So when it's in sampling configuration, it's actually pointed above. For this, we point it out in the other direction, and we kind of spin the entire spacecraft around. And we're measuring a property called the moment of inertia. We have actually already done this prior to initiating the TAG sequence today. So we know what that property is when the TAG SAM head is empty. Now we're going to be able to do it, hopefully, when it's full of asteroid regolith. So we're only looking for small differences in this property as a result of this experiment. And the precision, just like everything on this program, is phenomenal. We're talking tens of grams of precision on a measurement on a spacecraft hundreds of millions of miles away that just picked up this asteroid sample. The minimum that we're looking for is 60 grams, or about 2 ounces.
MSA on OREX Ops. Attitude control system has transitioned to touch and go mode.
Right, spacecraft's getting ready to make contact with the asteroid surface here. So the sample mass measurement will tell us if we have 60 grams or more of material, and that'll happen on Saturday later this week.
Excellent. Okay, Dante, this is it. You know, the engines have given us a push in the right direction, and OSIRIS-REx is on course to make touchdown on an asteroid. So we're going to listen to the flight controller calls from MSA, but before we actually touch the surface, it's a great time to visit our social media desk again. So, James, what's going on?
Yeah, thanks, Michelle. So you've been hearing those call-outs from Dale over the loudspeakers about those NFT images processing. It'd be awesome to actually grab a camera and make the trek out to Bennu to photograph it up close in person. But, you know, as we've mentioned, Bennu is a little bit far away from us right now, on the order of 200 million miles away. But don't worry, here's something OSIRIS-REx can deliver to you right now from the comfort of your own home. If you're on Instagram, you can head over to @NASA Solar System. We have 2 AR filters that you can use on your social media stories. This first one's called OSIRIS-REx and You and features OSIRIS-REx playing tag with Bennu around your head. The second one is called To Bennu and Back and allows you to place an asteroid wherever you are, at home, at school, bring an asteroid with you. So I understand we actually have a question coming in from Instagram from Mauricio, who asks, how do you manage the force back from touching down? I mean, the moment the spacecraft touches the surface, it should experience a similar force in the opposite direction. How do you manage that? Well, thanks Mauricio. So the team actually thought ahead for this one when designing that sample arm. They actually added the spring-like mechanism to it that you can think of a bit like a pogo stick. If that sample arm were rigid, when contacting Bennu, it would stop its downward motion, and when firing the gas bottle to stir up a sample, we would just kick right back off into space, as Bo Bierhaus had mentioned earlier. But since we have that spring, you can think of it like a pogo stick.
We are collecting tons of images right now, but we simply don't have the data rate to get them back to the Earth in real time. So they're just getting banked into the spacecraft's memory, and we're going to start looking at those later tonight and have them available for everybody tomorrow morning. So this is just a simulation of the field of view of the SAMCAM, the sampling camera, part of our OCAM's camera suite. It has a clear shot of the TAGSAM collector right in the middle of its field of view. You can actually see the lower end of the TAGSAM arm here.
OREX MSA on OREX off. OREX is descending below 25 meters.
Okay, we're getting really close. And I want to remind you, it's the 5-meter crossing.
Yeah.
That's the really critical one. We're only a couple minutes away from that. So the spacecraft has one key decision left to make. It's calculating right now the probability that it's going to come down either on a hazardous area, as we defined on that hazard map, or in a safe area. So we may, at 5 meters, the spacecraft may decide that it's hazardous and it's going to back away, allowing us to live the tag another day. So to me, all my senses are on that call out right now.
Yeah.
I really want to hear that we are go for tag, so that's just a couple minutes away here.
And of course, remember that that was planned for. That
That's right.
It has to know it's safe, otherwise it's going to back up and try again another time.
That's really how we solve the amazing challenges that this asteroid surface presented to us. You can see here that this is a pretty daunting terrain that we're coming down here. There's giant boulders all around the Nightingale site, even some large rocks inside the crater that we do not think the spacecraft would survive, at least with the ability to return back to Earth if it made contact. So it is there to protect itself first and foremost. Safety is always first, but we're feeling pretty good. Everything's gone really well today, so I would say things are looking great for a tag, but of course the spacecraft is the one that gets to make that decision.
It's just amazing. You know, we've been rehearsing this event, all week long, all the different mission calls and milestones, but then to actually be here tonight and realize that this is going on 200 million miles away.
That's right, yeah. I'm pretty excited.
So, I mean, there were obviously a lot of firsts in this mission.
OREX MSA on OREX ops. OREX has processed its next message. Position uncertainty is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%. Tag lateral velocity is 0.2 millimeters per second.
Oh my God.
Tag vertical velocity is 10.2 centimeters per second.
That sounded really good.
Yes.
So it sounded like the hazard map calculation looks really good. That we're coming down in a green area. We're going to make contact with the asteroid surface.
Well, so remember how historic this is NASA's first mission to retrieve a sample from an asteroid,
Yeah.
a pristine part of the solar system.
That's
Just
right.
look at that animation now. So we're looking
I'm looking at the team. I think that, I think we can see everybody is laser focused on what this spacecraft's going to do. So I say let's let this play out. But those calls were really great. That was great news from Dale.
Yeah. Even more accurate than we'd hoped for in some cases.
Everybody seems happy.
Yeah. So I guess there were obviously a lot of firsts in this mission, and there was a time when you said a lot of what ifs basically. I mean, what if we could actually send a spacecraft to an asteroid? What if we really could bring back a sample of the solar system from billions of years ago? Do you remember where you were when those what if
OREX
questions?
MSA on OREX ops. OREX has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
We're going in. We're going in.
Touchdown declared.
All right.
Sampling is in progress.
Oh my gosh, we're there, folks. That was amazing. I mean, I don't know if you saw the team here, but they just kind of blew up. They went from being steely-eyed to like celebrating the Super Bowl. So, it's all good. This is amazing. So congratulations, everybody. I know that Dante and Dr. Zabrukin are right here. And Dante, you somehow got over here pretty quick.
I sure did.
Congratulations. How you guys feeling?
Transcendental. I mean, I can't believe we actually pulled this off.
But I'm so excited about the team.
Yeah.
Hey, do you mind if I just bring up something?
Please.
Our friend Mike Drake is with us right now.
That's
the
right.
guy who came up with the mission at the beginning, and we're thinking of him. He's no longer on Earth, but I feel him right here.
I agree. He's with us today, and I know he's incredibly proud of this team and everything we have accomplished. This is history. It's amazing.
God, I can barely speak. You know, I'm like shaking. How about you?
Absolutely. It's almost hard to process everything that's happening right now. It's overwhelming pride in this team and everything we've done to get here. I couldn't really have anything better to say about this group of people.
All safety systems, I can confirm that the backaway burn is...
OREX MSA on OREX off. Sample collection is complete, and the backaway burn has executed.
All right.
We're on our way back.
Now, Dante, that was actually a really important call. We were celebrating on the tag, but that was actually probably even more important call. Why is that?
The pyro bottle's fired, so Tag Sam operated. The backaway thruster's fired, so we're safely moving away from the asteroid surface. The spacecraft did everything it was supposed to do. So we did it. We tagged the surface of the asteroid, and it's up to Bennu now to see how the event went.
What does this mean to NASA?
Oh, I mean, this is key milestone of this. Now it's a few days, right? To figure out how much we caught of this amazing sample that we're thinking about for decades. But I think this is just, I'm so proud of this team. Hey, team.
Oh, my goodness.
Oh, my goodness.
Well, I got to tell you, this has been a fantastic day, a fantastic journey. We're so proud of both of you for being here and supporting that team. We're going to get back over to the stage and Michelle, but some really good news. So back to you, Michelle. Thank you.
This is one of those moments we're all aware of COVID-19 because I want the hugs and the high fives and everything, but we're all going to keep each other safe. There are lots of super excited people all over who want to share in this moment and share their congratulations.
No kidding.
So let's take a moment to hear a few words from three institutional leaders who couldn't be here tonight, but they're cheering on the team on behalf of so many supporters.
Hi, everyone. Dennis Andrusick, Goddard Center Director. I am just so excited that OSIRIS-REx is collecting a sample from the surface of Bennu. The tag is just the pinnacle of the mission so far. Getting the sample back to Earth is obviously going to be a great event of the entire mission. But I got to congratulate Dante. You and your team, your project management skills as a PI, just superb. Rich, the operations team, for getting us to where we are, and Lisa Callahan for the awesome Lockheed Martin team, in getting OSIRIS-REx to where we are. And building a great spacecraft and returning it to Earth. Go OSIRIS-REx.
Today's an exciting day. As OSIRIS-REx begins its descent to Bennu, the nation is looking forward to the news of a successful tag event. OSIRIS-REx team members have been working on this project for more than a decade, and the work being done is hard, and it's complicated, and it's necessary. Understanding the makeup of Bennu will help us better understand our universe and how to protect our most important asset in space, Earth. I want to wish the best of luck to the entire OSIRIS-REx team, including our partners at the NASA Goddard Space Flight Center, the University of Arizona, and especially the mission operators and engineers right here at Lockheed Martin. Go OREX!
The University of Arizona is incredibly proud of its long tradition of excellence and leadership in space exploration. I'm thrilled to see the OSIRIS-REx's mission's achievements carried this tradition forward today with NASA, Lockheed Martin, and all of our incredible partners.
Congratulations to all of the OSIRIS-REx mission team members. You have shown the world how our determination, creativity, and talent can advance the capabilities of our entire nation. And I can't wait for the amazing science we will see with the sample return in 2023.
Okay, well, we are here live after some excellent news. I'm here with an exultant Dante Loretta from the University of Arizona. So one more time for our audience out there, explain when we know we'll have a sample.
A little overwhelmed right now, Michelle, I have to say. It's been pretty intense several minutes here. I can tell you that everything went just exactly perfect, which is kind of the hallmark of this team. We have consistently beaten expectations over and over again. We have overcome the amazing challenges that this asteroid has thrown at us, and the spacecraft appears to have operated flawlessly. We made it down to the asteroid surface. We were in contact. The gas bottles fired. We don't know how long we were in contact with yet. That's some reconstructed information that we're going to have to put together over the next few hours as the data come in. We backed away successfully from the asteroid surface. The team is exuberant back there. Emotions are high. Everybody is really proud, and we have some work to do to determine how much sample that we have collected. The next thing that I'm going to be looking for is once the spacecraft cools off, it probably got pretty warm as it approached the asteroid surface, so it needs to get rid of some of that excess heat. It's got to get those solar rays back onto the sun and get power positive. Once it's stabilized, it's going to point that high-gain antenna at the Earth, and we're going to start bringing that data back. And those SAMCAM images are going to tell us an enormous amount of information about how the events of today went. We're going to be looking at a whole series of images as we descended down to the surface, made contact, fired that gas bottle, and I really want to know how that surface responded. We haven't done this before, so this is a new territory for us. And the whole science team, I know, is really looking forward to that information. For one thing, it'll tell us the likelihood of sample collection, kind of a probabilistic assessment. Probably be a lot of science that comes out of that as well.
Yeah, well, listen, I know you want to be back there with your team. It's going to be a long, hopefully happy night for all of you as more data comes in. Thank you so much. It's been such an honor to be with you.
Thank you. Thank you, everybody, for a great evening. And kudos to this team. It's an amazing experience.
Oh, wow.
And history was made tonight.
Absolutely. Sure. So, you know, what we're going to do now is actually take a closer look at this beautiful terrain that we've actually sampled. We've identified over 1 million asteroids in the solar system. But remember, Bennu is what's called a NEO, a near-Earth asteroid. So instead of orbiting in the main asteroid belt between Mars and Jupiter, it has an orbit fairly similar to our own planet, Earth. And it not only gets our attention because it's so close to Earth, but also because we believe it may be one of the older bodies in the solar system with a wealth of information about how the solar system and life began. Let's take a closer look at the subject of all of this activity, all of this joy tonight.
Thank you.
Let's take a tour of Bennu.
In December 2018, after traveling for 2 years, 101 days, and over 1.2 billion miles, NASA's OSIRIS-REx spacecraft arrived at its target, near-Earth asteroid Bennu. OSIRIS-REx is the first mission to explore this primitive remnant from the origins of the solar system, designed to study the asteroid and return a sample to Earth. Bennu is a dark, diminutive world, roughly the height of a skyscraper, and now the smallest body to be orbited by a spacecraft. Prior to arrival, it was known to have low thermal inertia, a characteristic of fine-grained materials like sand. An infrared spectrometer on OSIRIS-REx confirmed this property, leading scientists to expect a predominantly smooth surface. But the first close-up views of Bennu delivered a major surprise. In exquisite detail, the mission's cameras revealed an unrelenting rockscape dominated by boulders. By combining these images from OSIRIS-REx with its laser altimetry data, we can take a tour of Bennu's remarkable terrain. The first stop is Simurgh Saxum. This prominent boulder defines the asteroid's prime meridian and serves as the basis of its coordinate system. In Persian mythology, the Simurgh is a large and benevolent bird and the possessor of all knowledge. Saxum is Latin for stone. To the northeast lies the largest boulder on Bennu. Measuring over 300 feet in length, rock Saxum is a colossus longer than a football field. It is also rich in a type of iron oxide called magnetite, which was used by mariners as an early form of magnetic compass. In Arab folklore, the rock is an enormous bird of prey that can clasp elephants in its talons, as well as stranded sailors like the hero Sinbad. Continuing northeast over the equatorial ridge, we arrive at Gargoyle Saxum. This striking boulder is among the darkest on Bennu, though it clutches a much brighter rock that is about the size of a person. In medieval legend, gargoyles are dragon-like, winged monsters that can breathe fire and that guard cathedrals from evil spirits. Our next destination takes us far to the east. At the northern end of a small crater lies Ocypete Saxum, a comparatively bright boulder measuring about 33 feet in diameter. Ocypete Saxum is located near one of 3 sites where Bennu ejected small particles into space in early 2019, displaying its dynamic and evolving nature. In Greek mythology, Ocypete is one of the 3 harpies, the half-maiden, half-bird personifications of storm winds, who would carry evildoers away from the earth. In the creation stories of ancient Egypt, the universe began as a formless, endless expanse of water. From this primordial sea arose the primordial mound, Benben. It was upon this rock that the god Atum settled in the form of the Bennu bird and sent forth the call that shaped creation. The story of Benben harkens to the mounds of fertile silt that once emerged from the receding floodwaters of the Nile, and it provides a fitting namesake for the tallest boulder on Bennu. Protruding by over 70 feet, Benben Saxum is so tall that it was first detected from Earth. Now, we can appreciate this monumental feature in detail using data from OSIRIS-REx. The final stop on our tour is a cluster of exceptionally bright boulders scattered across the southern hemisphere. They bear the spectral fingerprint of pyroxene, a mineral found in igneous rock that is unlikely to have formed on Bennu. These boulders most likely originated on the large asteroid Vesta and were delivered to Bennu's parent body through meteoroid impacts. Although it is small in size, asteroid Bennu has proved to be a fascinating world, abundant in geographic features that have defied our expectations. Thanks to OSIRIS-REx, we can now explore Bennu to uncover its composition, its evolution, and its ancient memories from the origins of the solar system.
And if everything has gone right tonight, a little bit of Bennu will be coming back to Earth in 2023. So let's get one last visit with our social media desk. James, what's going on?
Yeah, Michelle, I've got goosebumps. I really can't even begin to fathom that we just tagged and collected a sample from this asteroid 200 million miles away. I know I'm going to want to relive the events that just unfolded tonight. I'm sure you will as well. So once again, we have that 360 video up on our NASA Goddard YouTube page. Go check it out and put yourself right where the action just happened a couple minutes ago. It's truly mind-blowing stuff. I also want to check back in with that Twitter poll that we put out at the beginning of the broadcast. And we were asking you how much material you think we just got from asteroid Bennu. So remember, we're looking for at least 60 grams, but that sample container can hold up to 2 kilograms. So you guys are saying that a candy bar size of sample? I like the optimism. Let's hope we actually pack that container to the max and bring all the sample back home. But any sample we get back is truly magical and will help us learn more about the solar system and our origins here. So keep at us on the hashtag to Bennu and back. We're excited to keep this conversation going as we look to bring that sample all the way back from Bennu here to Earth in 2023. So back to you, Michelle.
This is one of these evenings where it's such a privilege and a pleasure to be working for NASA and for the idea of scientific exploration. So what we've been doing all evening is seeing the joy, seeing these people that have worked on this for decades. But you have to remember there's a real reason we're going to look at these asteroids. We think we actually might be coming back with a baby picture of what the solar system was like, of what our chemistry was like billions of years ago. We're looking for our own origins out there, and that's why we've gone so far to bring a bit of Bennu back. This has been an incredible evening. The adrenaline is slowly beginning to slowly go down, and there's going to be a lot of celebration and a lot of work in the coming hours. So from Lockheed Martin Space here in Littleton, Colorado, I'm Dr. Michelle Thaller. Good night.